My name is Albert Benseny Cases, and I'm a senior quantum control engineer here at Q-CTRL. Today, I am bringing you an update to the syntax for building graphs in Boulder OPAL that we think you'll really like. In particular, this will affect how you can create and manipulate piecewise constant objects, what we call TensorPwcs in Boulder OPAL, and sampleable objects, what we call sdfs in Boulder OPAL. Here I have a notebook that performs a simple optimization using Boulder OPAL. I start by importing the necessary packages and starting a session with the Q-CTRL API. I then define the single qubit Hamiltonian that I will use in this example. It consists of 3 terms, 2 time-dependent terms that I will try to find optimal controls for to implement, for instance, a Y gate. And the last term is a constant detuning term. Then I define some standard matrices and physical constants and parameters that I will use in the optimization. So for instance, the number of segments in each pulse, the duration of each pulse, and the maximum value that each of the controls can have, as well as the detuning in the system. I can now move on to building the graph. As usual with an optimization, I start by creating some optimization variables that I use to create a piecewise constant signal, one for each of the 2 signals in my system, the omega term and the alpha term. From these, I can now create some piecewise constant operators by pairing each one of these 2 signals with the corresponding operator by using the PwC operator operation. In the case of the detuning, because it's a constant term, I just use constant PwC operator. Finally, I can create the total Hamiltonian by using PwC sum and passing the 3 different terms to it. With all of this, I can now calculate what's the infidelity in the system by using the infidelity PwC node and passing the Hamiltonian, which operation I want to perform, and the name that I want to assign to this node. I can finally run the optimization by using the calculate optimization function and passing the graph and the node that I assign as the cost function, in this case, the infidelity. If I run this cell, I will see that Q-CTRL is able to give me some pulses that give me a very small infidelity. What we have recently been working on is the ability to simplify some of this code that I've used when building the graph. For instance, you can use regular arithmetic operations between PwC and SDF objects. So in this case, when I am adding the 3 terms in the Hamiltonian, instead of having to use the PwC sum operation, I can just use the normal addition operator and add the 3 terms together. You can also do operations between PwCs or SDFs and tensors. So in order to create a PwC operator, you don't need to use the PwC operator operation. You can just directly multiply the signal by the tensor or the array. Finally, because operators and PwCs can operate together, I don't even need to create a constant PwC operator for the detuning. I can just create it as a NumPy array, and the sum will take care of converting it to a PwC operator. So now I can see that I can use very natural language, very similar to what I would use when writing down the formulas, to create all of these terms inside of my graph. If I now execute this graph, I will obtain very similar pulses as before that will also perform very well, giving me very, very small infidelities, because this graph that I have just built is completely equivalent to the one that we had before. If you want to learn more about how to create graphs and run optimizations, I encourage you to take a look at our user guides in our documentation. In particular, the Setup Quantum Systems and Optimize Controls user guides. They will teach you all that you need to know to find optimal controls for your system. You can also look at our application notes where we show how to use Q-CTRL optimized pulses to improve the performance of logical gates in superconducting devices and other systems. Here I have a notebook that is set up to run a simple quantum simulation using Boulder OPAL. First of all, I show the system that I'm dealing with. Again, a single qubit Hamiltonian. However, this time I will focus on these 2 time-dependent terms and how to implement analytical expressions for both of them. I will simulate a Landau-Zinner transition in the qubit by sweeping the detuning alpha in the system while applying a pulse in the Rabi coupling between the 2 qubit levels. As before, I defined some standard matrices and physical constants that I will use in the simulation, as well as the initial state of the system. I can then move on to creating the graph. As you can see, the graph is still missing the part that creates the Hamiltonian. I will show you how I do this in a second. The rest of the graph just calculates the unitary time evolution operators, applies them to the initial state, and exports the pulses. The graph is then executed, and the results and the pulses are plotted. Let's go back to the missing Hamiltonian. I will show you how to create it from scratch using the analytical pulses that we had defined above. To achieve that, we have created a new node called identity SDF, which returns the function f of t is equal to t. I can just call this object t because it represents time. I can now then apply different mathematical operations to this SDF to create any analytical shape that I need. To be able to do this, we have updated all of the nodes in Boulder Opal that implement mathematical operations to also accept piecewise constant and sampleable functions. In this particular case, I can just create the analytical pulses by using arithmetic operations and the sine and cosine functions. And as I did in the previous example, I can use natural arithmetic operations to multiply and add together the different terms in the Hamiltonian. And that's it. Now, if I run this cell, I can see that the omega and alpha pulses that I have defined follow the analytical expressions that I had defined above. These pulses implement an almost complete Landau-Zinner transition between the two qubit states. So, in this video, I have shown you some new features you can now use in Boulder Opal. You can apply arithmetic operations between PwC and SDF objects and between each of these and tensors. You can also apply mathematical functions to these type of objects. This update will allow you to build graphs using simpler, more natural code. Finally, you can now create SDFs representing analytical functions by applying these operations to an identity SDF. You can use these, for instance, to add modulations or envelopes to your filtered signals or create analytical pulses from scratch, as we have done here. We hope you will find these updates useful. To learn more, you can go to docs.qcontrol.com to find user guides explaining how to use the different features of Boulder Opal, such as simulating and optimizing quantum systems. If you want to check the details of the graph operations we have discussed, you can check the reference documentation for the Python package. Thanks for watching, and until next time.